have been developed for alkaline and acid electrolysis, as well as for storage of hydrogen. And it's interesting to note that the biggest planned hydrogen storage facility is going to be here in Utah, very close to where we are. But with respect to the formation of gas, because we are doing electrolysis, what we have is that the gases are going to be forming electrons. And these gases have very low solubilities. And the low solubility of these gases implies that as they form in the cathode and the anodes, they're going to produce bubbles. Now, the issue is that the more we want to generate gases, the faster we want to go, the faster we're going to get bubbles, and these bubbles block the electrode by blocking and decrease the currents. So we try to get more current and we get less current, and current is the rate of the chemical reaction. Now, this picture is for very large electrodes that you can see, but the truth is that most of the methods now usually used in electrolysis try to get maximum current density, maximum rate of the reaction by decreasing the electrodes that are typically expensive platinum particles into tinier and tinier particles. So electrodes that are a few nanometers are common now, and people are going to single atom catalysts. This poses several questions, and the reason why people go to single atom catalysts is because you have better relation of area to volume to mass of the platinum, and also because you have better catalytic activity. But this, to us, poses the question of what is the smallest electrode that can produce bubbles, and most importantly, what is the fate of the current if we have bubbles on these very small electrodes. Now, to understand this, a few years ago, there was no way to address it, but now there have been in the last decade experiments that are based on single electrodes. And these single nanoelectrodes are made by the group of Henry White, our colleague and collaborator here at the University of Utah. And what they are small capillaries in which you have glass. Inside you have a platinum electrode, and by heating you can make a very, very thin one. Then you cut it and you have exposed a platinum electrode that is just a few nanometers and is well characterized, embedded in a glass silica matrix. Now, when we look at these single electrodes, the way to characterize them in the lab is through a cyclic voltammetry. And for those of you that are not familiar, what we're doing in cyclic voltammetry is that we are moving the potential that is the driving force for the chemical reaction. It's like you're moving the delta G, the free energy, with the potential. And when you are moving the potential enough, you start producing, favoring the reaction that we're looking for in this case is protons goes to hydrogen. And the more the reaction happens, the higher is going to be the current. In this case, by convention, the current is negative, but larger magnitude of the current means that the reaction is going faster and faster. And this is because the driving force increases. But at one point, the current is so high that the supersaturation on top of the electrode, the amount of gas dissolving the immediacy of the electrode, is so high that a bubble forms. And this is a first order transition from supersaturated solution to a bubble. And when the bubble forms, the bubble completely covers the electrode and the current drops, as we expect. Now, there are two things that are intriguing about this. And one of them is that when you're looking at any of these potentials after the bubble drop as a function of time, the current is stationary. Now, the fact that the current is stationary, independent of time, can be understood from the point of view of the place where the bubble is and what would happen if the bubble tries to grow or decrease. Let's say that the bubble becomes too large and the bubble grows more, it's going to cover completely the electrode, and there's going to be no area of the electrode left for the reaction to happen. In that case, you have a feedback in which now the bubble cannot continue being fed by the hydrogen, and the bubble is going to dissolve. If, on the other hand, the bubble were to dissolve too much, then you have much more area exposed, and we have a very high driving force, and the bubble grows again. So there is a synergism between these two effects, and this homeostasis results in a bubble that is independent of time. But the bubble itself cannot be seen in electrochemistry. Only we can see the current that it generates. So this is the first point, that the current is independent of time. And this is not surprising. What was surprising and caught our attention is that the bubble, the current that you get, the stationary current, is independent of the potential. So you have a potential after the bubble has formed, and then you increase the potential, and you increase the potential, and you increase the potential, and the current is always the same. So despite the change in the potential, you cannot extract more current under this regime. The second thing that was quite surprising to us was that this current is also independent of the size of the electrode. And for this, I'm going to illustrate with this figure that shows the residual current, the one you get after the bubble has formed, for electrodes with radii that go from a few nanometers, 3 nanometers, to about 50 nanometers. And in all this range, you have some variability because the electrodes are all different, but the current is always 1 nanoampere plus minus 0.5 nanoampere or 2 nanoamperes. So this is a very constant current, and this is not what we expect if we know that the rate that the reaction is happening on the boundary, and we expect that it will go with the circumference. So we were intrigued with this and with the question of what happens when we make smaller and smaller the electrodes that are difficult to explore electrochemically. And to address that, we use molecular simulations. Now, this is a case in which molecular simulations have to address two completely different kind of rare events. One of them is that the bubble formation is a phase transition, and we need to be able to describe the transition between supersaturated solution and the formation of a bubble. And the other is that we have an electrochemical reaction that is driving this transition. This is the reaction in which a reactant, in our case, we're going to assume that is water, but could be the gas, the protons dissolving water are reacting at the electrode and are producing a gas. So how do we couple these two? Has to do with in principle, you can couple these two using, for example, density functional theory. The problem is that the cost of these calculations is extremely high because the electrodes are several nanometers inside. Then we have to have a support. The electrode is the one in gray. Then we have to have a support. We need to have water. We need to produce electrodes. We need to produce gas. And all this requires pretty large-scale simulations involving at least 20,000 particles, but usually much more. So the way we address this is by combining molecular dynamics with coarse-grained models that are based on short-range interactions, and because of that, they are about 100 times faster than all atom state-of-the-art simulations, with kinetic Monte Carlo to produce the reaction at the interface. The molecular dynamics allows us to evolve the system and have the phase transition, and the kinetic Monte Carlo is the one that produces the chemistry in accordance to the potential of the electrode. So I presume that many of you are familiar with molecular dynamics or have heard many talks about this, but the part of kinetic Monte Carlo is a little bit different. So what we're doing is we're modeling the electrochemical reaction at the electrode as if it were a stochastic process with probabilities consistent with the reaction rate of electrochemical reactions. This is called Battle-Vormer kinetics and is given by the reaction, the equation that says the reaction rate forward to produce water plus electron, the electron is not really there, forms gas, depends on the reactivity of the system. In this case, the reactivity is the one we are using is the one experimentally obtained for hydrogen and platinum. Then there is a tunneling effect that says that only molecules that are close enough to the electrode are going to react. This coefficient beta is about 1 angstrom, so only water molecules that are within 1 to 5 angstroms react in the electrochemical reaction. And the most important part is that we have a term that depends on the electrochemical potential. So in this term, E minus E0 is the over potential, how much we're applying over the equilibrium potential E0, that for simplicity we're going to consider 0, and we're going to be reporting this potential. And then 1 minus alpha is the asymmetry of the reaction forward and backwards, but alpha we take to be 0.5 in agreement with most experiments. And then this is just the number of electrons exchanged, Faraday's reaction constant, the constant of gases, and the temperature. So what we're doing is using this constant forward and the equivalent backwards, we are having a probability of transforming any water molecule in the immediacy of the electrode into gas, and then at the same time, any gas molecule in the immediacy of the electrode into water. Of course, the reaction is biased in one direction or the other depending on the potential. So we combine the MD with this to address several questions. The first one is, how do the bubbles nucleate on the electrodes? And this is because there have been some discussion of whether the nucleation is induced by the electrode or it's just that there is so much supersaturation that the nucleation is homogeneous, just in the solution. And the second question here is whether all bubbles that form on the electrodes lead to stationary states. So why is the current going down to stationary state and doesn't continue increasing? So to understand this, we have to take into account that the nucleation of the bubble is a first-order activated process. So what we have essentially is that an electrode in which gases are going to be forming is a state that can be supersaturated. It has higher free energy than the electrode with the bubble. And this state that is supersaturated has a probability of going forward and forming the bubble, and this is given by a barrier, and this barrier depends on properties that are very well established. One of them is the contact angle of the gas on the electrode, and this physically depends on the binding free energy, how much free energy you need to move the bubble into the electrode. If this binding free energy is negative, then this is going to promote the barrier for nucleation. Then what we have is the surface tension gamma of the solution bubble interface. This is because the solution interface is what gives you the cost of forming this new phase that in principle is more stable. And then the driving force that is given by the density of the gas in the bubble, RT, and the important value is the log of the supersaturation, how much more we have of gas compared to how much is given by the solubility. So the supersaturation is the driving force, and gamma is the one that goes against, and the electrode can help if the binding free energy is negative. From this, it comes that the stronger is the surface binding to the bubble, the lower is going to be the barrier. And this is something that we can check now in simulations on whether it is the case and what is the impact on the type of bubbles that you form on the electrodes. So what we did is we investigated the interplay between gas electrode and water electrode interactions in the control of the process of nucleation of the bubbles. What we can see is that if the interactions between the bubble and the interactions, I'm going to start with this one, solution nanobubbles. If the water electrode interaction is strong, then the water will be very attached to the electrode. And if the gas electrode interaction is weak, that means that this is a very hydrophilic electrode. This extremely hydrophilic electrode will produce bubbles, but these bubbles are going to be such that they are not bound to the electrode at all. And this is because the binding free energy of this bubble to the electrode is positive, and because it's positive, it cannot promote heterogeneous nucleation. So this is a case in which the bubbles are formed, but they don't produce a stationary current because they never block the electrode. This is not what is seen in the experiments. The other extreme example is the case in which the electrode interaction is weak, the electrode is sort of hydrophobic, and the electrode has high affinity for the gas. In this case that we show here in red, the interaction between the surface and the gas is extremely strong. The binding free energy is so strong that induces pre-wetting, and you can form a bubble that is completely flat, contact angle 0 on the electrode, even before you get supersaturation. So any gas that is in the solution is going to try to bind. And when it binds, it blocks. And in this case, you don't need to apply supersaturation to get to the formation of the bubble. This is not what they see in the experiments. The final case, that is the one that they see in the experiments, is the formation of a surface nanobubble in which you have blocking by the bubble. And this is what you get when you have comparable, although more favorable, interactions between the gas and the electrode and the water in the electrode. So in this regime, the bubble is going to form at the electrode and then is going to remain attached. What we conclude from this study is that all bubbles that attach to the electrode and block the electrode requiring supersaturation, that is the case that we see in the experiments, are heterogeneously nucleated, because if they were homogeneously nucleated, as some people speculated, they would not be able to attach and will not block. So we can answer with this one of the questions that our collaborators had. Now, there are many possibilities of gas-platinum interaction that are going to result in the formation of bubbles that are attached to electrodes. What we are working with is a model that has interactions that are mimicking the interaction between nitrogen and platinum, and in this case, the critical nucleus at the top of the barrier for the formation of the bubble contains about 30 molecules. And this size is in good agreement with about 40 molecules that were deduced using nucleation theory for the formation of nitrogen on platinum in the experiments of the white lab. Now, the other thing that matters is that when we start the formation of the initial cluster, the system is so small that you have a very high Laplace pressure. And this Laplace pressure that is related to the existence of curvature in the system is going to make that the initial bubble is actually more like a dense liquid than a very, very low dilute gas. That's why you see that it looks like a liquid forming on the electrode. Now, we have shown with the simulations that the experimental conditions observed so far all correspond to heterogeneous nucleation on the electrode. But this is not the same to say that the bubble cannot move away from the electrode and free the space for more current to be produced on when we increase the potential. So what is that makes the bubble stay on top of the electrode and not move away? What we show in this case is that the bubble remains pinned to the electrode because the pinning has to do with the differential wetting of the electrode that favors the gas and the outside substrate, in this case silica, that favors water. So we have that the bubble is formed on the electrode but cannot grow outside because the black area has unfavorable wetting properties for the gas in the bubble. If we remove this condition by making the wetting of the electrode and the silica the same for water and for the bubble, so we make the gas interactions with the gray and the black identical, and the blue interactions with the gray and the black identical, then what we find is that the bubble is formed on the electrode because it's where the reaction happens, but then it can be moved. And in that conditions, the bubble continues growing, the current is not stationary, and we don't find the stationary state like shown before in the experiments. So the stationary state is controlled by the differential wetting between the substrate and the electrode where the bubble is going to form. Now, that explains how the bubble forms and why it stays in place. Now we are going to address the question that we found the most intriguing, that is why the current remains constant with the potential and with the size after the bubble has formed on the electrode. To go back to the place where the current is generated, we have to take into account that as the bubble has formed and is covering all the electrode, then the only place where the reaction can happen, where the water can get close enough to the metal that the reaction can proceed by this tunneling distance, is in the very boundary. So if we look from the point of view of the electrode and we map all the reactive events, they always happen at the boundary, what is called the three-phase interface between the electrode, the solution, and the bubble. Now, this is what is called the three-phase line, and this three-phase line is fluctuating because is a soft bubble on top, and when this gets uncovered, there is where the reaction is going to happen with a certain probability. But now, when we look at this, it may look like the current should be proportional to the circumference of the electrode, because if we have more circumference, we have more places for the reaction to happen, and this suggests that the current is going to increase with the electrode size according to the radius. However, this is not the case. I showed you before, and let me tell you now with more evidences. After the bubble has formed and covers the electrode, the experiments show that the currents drop to a value that is independent of the electrode size. So, for example, in this case, we have an electrode that is 10 nanometers in radius, and the current goes up, and then when the supersaturation is high enough, the bubble forms, and you get 1 or 2 nanoamperes. Then you go larger electrodes, 80 nanometer electrodes, and the peak current is always proportional to the area because it's happening everywhere, the reaction before the bubble forms. But as soon as the bubble forms, the peak current goes down to essentially the same value. And this is what we see in the experiments. We have done the same in the simulations, and we see the same effects. The larger electrode for which we can build a voltammogram is one that has 7 nanometers in diameter, 3.5 nanometers in radius, and you can see the same behaviors in the experiments. The current goes up, now in blue, as we sweep forward and we don't have any bubble on the electrode. we continue increasing the current until at one point it drops because the bubble has formed. And when the bubble forms, the current now becomes independent of the potential, and believe me, also is independent of the size of the electrode. We have seen this in the simulations. And then we can compute the voltammogram, now dissolving the bubble from the solution into the solution. By the way, this voltammogram that I'm showing here is the first ever computed in molecular simulations for any material. So now we know that the currents are independent of the size and also are independent of the potential. It has been conjectured before that the invariance with the potential of the current had to do with the bubble being exactly the same no matter how much potential you apply to the system. We can now address this with simulations, because in the simulations we can see the bubble that in the experiments cannot. And what we can tell is that when the bubble is in the regime that the potentials are high, indeed we see that the bubbles have always the same stationary current, but you can tell that the size of the bubbles are different. So what we see in the simulations is that the size of the bubble always increases when we increase the potential. So the size is stationary, but is not independent of the applied potential. Now, what we see is that it increases monotonously the size of the bubble, but in terms of the currents, what we see is that there are two distinct regimes. If we have potentials that are relatively low, what we have is the bubble does not fully cover the electrode, and when it's growing, it's still growing, keeping the contact angle. So in this regime, the bubble first covers part of the electrode, we apply more potential and covers a little bit more until it finally covers all the electrode. And under these conditions, because of the amount of exposed area varies with the potential, what we see is that the current increases as the potential is increased. This we call the leaky regime, because not all the molecules that are generated on the potential on the electrode enter into the bubble. Some of them go directly into the solution. If we now go to very high potentials, and very high is just 200 millivolts, it's not really very high, what we see is that now the current is independent of the potential, but the bubble still is growing. In this case, the simulations show us that the bubble is growing, but because already is pinned by the electrode and cannot grow further, what it's doing is it's becoming fatter and fatter. And when it's becoming fatter and fatter, what you have is that anything that reacts on the boundary of the electrode is bound to get inside the bubble and then go into the solution. This is what we call the tight regime, where all the molecules are processed through the bubble. Now, these two regimes that we identify in the simulations also exist in the experiments. They're not easy to see when you are going up in the formation of the bubble, because there is in the sweeping forward, there is no bubble until it crashes at very high supersaturation. But when we dissolve the bubble, what we see is that the potential does not change the current, and then at one point, when the potential is low enough, we go into the same as we predict there, that the current diminishes. So only in the tight regime, the red area, all the gas enters the bubble. Can we use this to explain why, in these conditions, the current is independent of the potential and the size? So this is the only slide with equations, and I would like to emphasize that this is a very simple model that captures exactly what is happening in the experiment. We start with the assumption, that is the one of the experiments and the simulations, that we are in a stationary state. Because we have a stationary state, the number of particles, the number of gas molecules, does not change with time inside the bubble. So the bubble has always the same number of molecules. But this results from two processes. The current is the flux of molecules inside of this bubble. So the current divided the number of electrons and the Faraday's constant tells us how many particles enter the bubble. And this integral tells us how much is the flux of the gas across the interface of the bubble multiplied by the area of the bubble. So what we have is that the two are exactly compensated. So we have generation and diffusion out. Now what we can do is we can write the flux, this diffusive outflux that now I write as the change in the amount of gas as a function of time, depends on the diffusion coefficient of the gas, how fast it can go away from the surface of the bubble, the radius of the bubble, and then it also depends on the driving force, the concentration at the surface of the bubble minus the concentration in the bulk. This is the driving force for the flux of gas outside of the bubble, and this is multiplied by a factor that this factor that we see there has to do with the contact angle, the shape of the bubble. Now we can further consider that the concentration on the surface of the bubble is given by Henry's constant that probably several of you have studied or teach in general chemistry and physical chemistry, Henry's constant, multiplied by the pressure of the gas at the surface of the bubble. And this is where the magic happens. The pressure of the bubble is the external pressure plus the Laplace pressure. And this Laplace pressure, it comes from the curvature. So the larger is the curvature of the bubble, the more flat, the lower is the Laplace pressure. But if the bubbles are very small, like in these nanoelectrodes, R is small, and then the Laplace pressure is 2 times the cost of the surface tension between the bubble and the interface divided by R. And what happens? Now we have an area term that is going to depend on the radius. And we have now a concentration that is going to be inversely proportional to the radius. And because these two cancel out, what we have is that at the end of the day, the rate of dissolution of the bubble, that is the same as the rate of replenishing with the current, becomes a constant multiplied by the diffusion coefficient, the surface tension, Henry's constant, and a factor that has to do with the geometry of the bubble. But absent there is anything that has to do with the radius of the bubble. So the radius of the bubble is not part of this equation. So what we can show with this is that we can explain why the current is independent of the size. And also is independent of the potential, because the only thing that changes with the potential is slightly the shape, but this function is a slowly changing function of the contact angle, so it's almost independent also on the potential side. So this is the explanation of why the current is independent. Now, this explanation that I say that is independent is actually assuming that the bubble is very small. Because if the bubble is very small, we can say that the pressure is just the Laplace pressure. And under these conditions, what we get is a straight line, so that the current should be always constant, independent of the size of the electrode. Now, if we are more realistic, if the electrodes are large, let's say 20 nanometers or larger, what we have is that the Laplace pressure becomes closer to the external pressure. And under these conditions, we cannot neglect external pressure, and we just put it back, and what we get is this blue curve that says that eventually, when the electrode reaches a micron size, you can get a residual current that is as large as the one that you get for a 3 nanometer electrode. But this tells us that if you increase the area of the electrode by 500,000 on going from 3 nanometers to 2 microns, you just double the current that you are going to get from the stationary state. So this clearly shows that it's better to use small electrodes instead of larger ones when we are operating under conditions that produce the bubble by nucleation and growth. What I showed you before, and supported by experiments, is that up to about 3 nanometer electrodes, 5 nanometers is the smaller that they were able to measure this individually in experiments, you can get that the current is independent of the size. But the question is, what happens if we go to smaller sizes? And these smaller sizes are actually the ones that are more relevant from the point of view of the experiments with catalysts in, let's say, electrolysis, because the typical nanoparticles used in electrolysis or in other electrochemical reactions are 1 to 3 nanometers in size. And this poses an interesting question, that is, what happens to the phase transition now that the size of the electrode is comparable to the size of the critical bubble, the one that we need to surpass to really form the electrode. We have to go through a critical point, a critical size. And now this size of the critical nucleus when we have a large system is about 2 nanometers. So what happens to the bubble and the current when the electrode size limits the bubble nucleation? We did this expanding into smaller and smaller bubbles, and this graph summarizes the current as a function of potential and electrode diameter. What you are seeing is that the diameter, as the size becomes smaller and smaller, we have the area where we don't have any bubble, this is before the nucleation of the bubbles, extends up to higher driving forces. And this is not surprising because as the surface of the electrode is not just containing the bubble, but it was an integral part of promoting the nucleation and diminishing the barrier. That means that if we make the electrode smaller, what we have is that at one point, the surface that is going to stabilize the bubble at the electrode interface is so small that you need to apply more supersaturation, and you achieve this by applying more potential for the electrode to be able to produce this phase transition. So the increase in the potential needed for the formation of the bubble is something that we were expecting. What we were not expecting is that the current becomes maximal when the electrode is about 1 nanometer. So the bluish area is the one that has the highest current, and it has a current that is at least 50% higher than an electrode that is, for example, 3 nanometers, 5 nanometers, 100 nanometers. So there's a maximum in the current when the electrode is about nanometers. And not only there's a maximum for this size, but maybe it's not so obvious, but there's a particular potential for which the current is maximum, and then it drops again. So this tells us already that there is a particular place where it's optimum to operate this system for electrolysis. We can get the maximum when we have 1 nanometer electrodes, and let me remind you that now a 1 nanometer electrode with a bubble on top can have as much current as a 1 micron or 2 micron electrode with the bubble on top. So this is a big improvement in terms of the current. And moreover, if we look at the deviations, what we can see is that the prediction from the theory is this black line, and the simulations are in good agreement. And then when we make the bubble, the electrode extremely small, going below 3 nanometers, what we see is that we start growing the currents in a way that is quite significant. This is where you can see that the current of micron size and nanometer size electrode are identical. This is even more pronounced if we consider the current density, that is the current divided by the area of the electrode, and is a typical way presented in electrochemistry. Of course, even when the currents are constant, because the electrodes are smaller, the current densities are going up. But having an electrode as small as 1 nanometer, we can get a 50% increase in current density in the reaction rates. So what's going on in this spot that is particularly good? What we find is that in these spots that are particularly good, the currents are high and the surfaces are covered by something that we would say is a very, very tiny bubble. But this tiny bubble is fluctuating so much because the system is very small that sometimes the electrode is completely covered and sometimes it's partially covered. So what we're seeing here is the cluster size, and this cluster size is the size of the bubble in the electrode. And for the smallest electrode in this point of maximum current, it has just about 15 molecules. And these 15 molecules, in average, they look like this. And you see there are big fluctuations at the interface. Likewise, when we go a little bit higher in potential, we still have larger bubble, about 40, 50 particles, but also, again, we have very large fluctuations. To put this in perspective, we have shown before that we were able to compute the cyclic voltammograms, that is the response of the current to the potential, and we show that even for a 7 nanometer electrode that is very small in diameter, we find the same behaviors for the large electrodes. We have an overshooting of the current because it's accumulated supersaturated gas on the electrode, and then the phase transition happens and the current goes down. So the going forward and backwards are going through different pathways. In the case of these small electrodes, the 1 nanometer diameter electrode, what we see is that the current going forward and the current going backwards are completely reversible. And this reversibility can be a purely kinetic effect that the barrier to form the bubble is very small, or can be because the transition is losing the first order character, that is that we are going a sudden transition from supersaturated to bubble, and it becoming a second order transition. So to understand whether this is the case, what we do is that to understand whether the transition has really lost the first order character, what we're doing is we look at the thermodynamics of the formation of the bubble. And this is because we can now write the equation of the free energy of the bubble as a function of the saturation, supersaturation, the cost of the interface of the area between liquid and gas, the cost of the interface between the gas and the electrode, the S is the electrode, and of course, because we are considering a system that the bubble is open to the solution and is controlled by a chemical potential of gas in the solution, what we're writing here is the grand canonical free energy, in case that you care about the thermodynamics of this. And the grand canonical free energy, we also have to take into account the pressure and the volume of the bubble. So if we write this is the thermodynamic formulation of the free energy of the bubble. What we find is that the profiles look as follows. When we start, we have, for a given supersaturation that is fixed in all this calculation, we have no electrode, no bubble at all in the electrode, but we have the supersaturation fixed. Then we find a first barrier, that is the barrier for nucleation I have shown you before in simulations. And this barrier for nucleation can be large or small depending on the supersaturation, and gives rise to the formation of the bubble on the electrode. This is the first minimum. Now, the second minimum would be that the bubble now can grow, because the gas is supersaturated, can grow and expand outside of the electrode, encompassing the full range of the material. But this is not possible because I showed you before that the bubble cannot outgrow the electrode, or it shuts down the actual generation of gas. So that means that although there is a hypothetical second barrier to outgrow the bubble outside of the electrode, the system is bound to fluctuate in this region and cannot go away. Now, what happens when we go for smaller electrodes? It has been shown before using theoretical approaches, density functional, classical density functional approaches, that when you are decreasing the size of confinement for a fluid, what you are actually doing is moving the liquid vapor critical point. And this is exactly the same. What we have is a supersaturated to bubble transition that is first order, and this transition is going to be moving, there is an end to the transition of a critical point, and we're going to be moving the liquid, the bubble to solution critical point as the electrode becomes smaller and smaller and smaller. And we can see that by looking at the free energy profiles as a function of number of particles for smaller and smaller electrodes. For 5 nanometer electrodes, we show that there's a minimum. Then I'm not showing the second part, there's a minimum also for the 2 nanometers. This is a first order transition with a small barrier. And then when we have 1.5 nanometer electrodes, you can see already that the formation of the bubble is such that now the bubble on the electrode has more free energy and is more difficult to form because there is not enough space for the bubble. And at 1 nanometer, the transformation is continuous, and you are trying to push the system forward when you apply more potential, but the system is not stable, and that's why we have so many fluctuations. So what we interpret is that on decreasing the size of the electrodes, what we're doing is we're moving the transition from first order with a very well-defined nucleation and growth and a barrier to something that becomes much flatter until eventually you cannot form the bubble anymore. And these fluctuations are at the heart of having a higher current in these small systems. So with that, I hope I have shown you that is the electrochemical generation of nanobubbles is a very interesting and, on the other hand, apparently simple problem that involves electrochemical reactions that are controlled by the chemical potential of the electrode, phase transitions, in this case, liquid saturation to bubble, nano confinement because the electrodes are small, and differential wetting that keeps the particles in place. And to understand how these different factors are playing together to produce bubbles, keep them on the electrodes, and control the currents, we have used molecular simulations using kinetic Monte Carlo for the chemical reaction and coarse-grained molecular dynamics to evolve the equations of motion of the particles, as well as analytical models based on thermodynamics, transport, and nucleation theory to interpret the results of the simulations and move them and generalize them to larger scales. What we have learned through this study is that surface nanobubbles are always nucleated through a heterogeneous mechanisms. They're always attached to the electrode, and that means that they are favored in the nucleation by the electrode itself. If the reaction is such that the nucleation is homogeneous, it happens in the solution, then the bubbles are formed, but they're never attached and they don't produce a stationary state. We also learned that the bubble is pinned to the electrode only if it is more hydrophobic than the surroundings. And this is the typical case, apparently, for hydrogen, methane, many other cases that have been tested in experiments, but it may be possible to unpin the bubbles and let them go away by changing the chemistry of the electrode or the chemistry of the surroundings to let the gas expand and not block the electrode when it's formed. We also showed that although the currents are independent of the driving force, the size and contact angle of the bubbles continues increasing, and this is what we expect. They're becoming larger and larger when we are driving more and more the reaction. And we have been able to explain why the current is stationary, why the stationary current is independent of size and potential by writing a very simple analytical model that equates the flux of gas into the bubble from the chemical reaction from the gas going out from the surface of the bubble. And we show under which conditions this is satisfied. And what we found is that this condition is satisfied for ranges that go up to even tens of nanometers, and then if you go to hundreds of nanometers, you get at most a doubling of the current of the electrode. So that means that we have a very broad range where we cannot extract more current, even if we make the electrodes pretty large. And finally, we show that for cases in which the electrodes are small enough, in which the size of the electrode is comparable to the size of the critical nucleus of the bubble nucleation, what we see is that we have to apply more potential to form the bubble, but not only we have to apply more potential, but when we apply this potential, we can extract more current. And this shows that if we were able to make small electrodes and have arrays in which these are separated enough, that is what people use, we are going to be maximizing the rates of gas-forming reactions without having to worry about the formation of the bubble and the catastrophic effect that they produce on the currents. And with that, I want to thank you again, and I hope that you have some questions that I can address. Thank you.
Questions? No questions from the live audience. Any questions at the internet? Let's see. Valeria, I do have one question about this combination of kinetic Monte Carlo and your ND simulation, right? So, how do you take into account the fact that when you do the KMC, you basically sample an event, but you have to advance time by a certain amount, which is not measured in ND steps. So if you want to do this a long time, so how do you take that into account, that you have a certain time that you take into account for some process to occur, some reaction to occur? So how do you do that?
That's a good point. So let me go back to this. What Maurice is asking is about this tau in the, what is the time? So for the potentials that we have, we can do this, we can advance that in each step of the molecular dynamic simulations, we evaluate whether there is a reaction or not. We have done this. But at the end, you don't need to make it happen every time. We can consider that the KF is more like 10 steps or longer, because the reaction rate is extremely small. Under normal conditions that we compute these voltammograms, you get about one reaction every 100 picoseconds or every 20 picoseconds at most. So these are very rare events. So you have a lot of freedom, and we have optimized this tau to be larger than the time step, but not extremely large. But it's something that we had to consider in the calculations. Yes.
Because actually, one of the things that we use KMC for is to be able to extend the timescales accessible to your simulations, right? So.
Yeah. Yes, in our case, we cannot, because the Monte Carlo does not add much cost to the MD. Originally it did, because we were computing a different way, but now actually the overhead from the kinetic Monte Carlo is less than 10% with respect to the MD. So the actual cost is mostly the molecular dynamics that we are already doing with coarse grain models that are 100 times faster than typical all-atom simulations. And the KMC is adding just a little bit more of overhead, because we have to evaluate for molecules that are in the immediacy in about 1 nanometer of the electrode, whether they have a probability the gas to transform into water and the water into gas. Because it's very short range, the chemical reaction, due to this beta being 1 Armstrong, this is a very small overhead. So we cannot extend the times truly, because still we are evolving the dynamic step by step.
Okay, so I guess I'm mentioning this maybe in a little different context when you look at, say, deformation of metals or something. Yeah. You have a catalog of different events that can occur, and basically by the KMC you can actually reach timescales of microseconds or even longer, exactly. Because you basically filter out the irrelevant vibrations of the atoms, right? Yeah. But that's not exactly what you're looking after here, right?
Exactly. In our case, this is the usual, what you are describing, the usual way of exploring with KMC, that you say, well, I'm having a kinetic of A goes to B, B goes to C, and I give values, and I proceed to evaluate these rates without any positions, without any equations of motion. But in our case, what we have is that we are copying the kinetic Monte Carlo only to produce the chemical reaction. The equations of motion are always there advancing so we have the fluctuations, we have the phase transitions. But yes, the one that you're describing is the most common use of kinetic Monte Carlo. Now, the scheme we're applying here, we can apply to other things. For example, I was the other a week ago in Nanobubble 2022, that is, of course, about nanobubbles. And there were some people studying the chemical reactions and the surface of hydrogen of a liquid-liquid interface, and a chemical reaction that produces a bubble. Now, in that case, it's not dependent on the potential, but you can reparameterize this same procedure to account for the chemical reactions and give a rate for the chemical reactions and produce nanobubbles at the liquid-liquid interface. So this scheme is quite general. We can also use it to do the position of metals and electrodes. We can also use it to produce another chemical reactions, electrochemical or not, that they are localized. It's a nice way to add reactivity to chemistry.
Okay. I think Munir's question. Maybe Munir,
cases, no?
Munir, would you like to ask the question with sound so that we can hear it as well?
It's loud?
Yes.
Okay. Thank you, Valeria, very much for the talk. Very, very nice as usual. My question is, was it really necessary to adjust the coarse grain parameters to get proper vacuum behavior? The reason is that because since the selective wetting is such an important phenomenon here, yeah. I wonder if the behavior is not that sensitive to the Hamiltonian at all, or.
Yes, it's not very sensitive. Actually, I am a lucky person, and we were lucky. We got them right. So we already had our reaction. We're making water into methane. That is sort of ridiculous, but we already have interactions between this water and methane and silica for some other studies, and we had to decide what was the gas platinum and water platinum interactions, and we selected these to be mildly hydrophilic and not too much, and we already got this spinning. You have to really erase the differences between the electrode and the silica quite a bit to get the bubble to expand into the surroundings, at least in our calculations. So I would say that there is a very, very broad range of interaction parameters that allow you to have pinning. And this may explain why in the experiments of Henry White, they form bubbles on platinum always. They form bubbles of hydrogen, CO2, nitrogen, I don't remember, like 6 or 7 different gases, with different chemical reactions, and the phenomenology is always the same. That's why that gave us confidence that we can invent essentially almost any parameters and we're going to get right. We had to go quite a bit far to get the case in which the bubbles do not care about the electrodes is quite extreme. So you see that it's one extreme and another extreme. Most of the results that have comparable interactions of gas electrode and water electrode are doing right. And silica is just much more hydrophilic. But let's say that you make the outside hydrophobic, and experiments you can do that by silanization. This is something that has not been published, but everybody has done. Then what you get is sort of, the current looks like it's erratic, because the bubbles are growing, they're moving outside, then they're coming back, and the current is going up and down. And you can see that in the experiments and the simulations too.
Thank you.
But it's very robust. That's why we can use it. So it's not very picky. Yeah.
Okay, so I have one last question. It may be really hard to do, but I found it interesting, this transition from going from a first order transition with hysteresis to something which is like a critical point, right? So there's a continuous transition from one to the other. Do you think you can define something like critical exponents for that? This critical point, would you be able to determine things like that, you think?
The fluctuations are dampened. I think that the question, so Evans, Tarazona, and Beto Marcoli wrote some extremely difficult to read papers on this matter in the 80s. And the issue is that I don't think that you have critical exponents anymore when you go to these conditions, because the fluctuations are dampened. So the disappearance of the barrier is straightforward. The magnitude of the fluctuations is always restricted by the actual size of the electrode. And I don't think that you can get exponents for this. But there were a lot of studies on this area in the 80s, and they may have already addressed the question, for what I can tell. I read the papers, they're just difficult. So it's one of these papers that you read again and again and again, and you wonder how many times I'm going to read it until I get it. There were many exponents there, but it's going to be challenging. Yeah. So that's why it's, this is one example in which the confinement leads to the demise of the first order transition. And people tell about this also for transitions in pores, but in many cases, I would say what looks like is a continuous transformation is just a discontinuous transition with a very little activation. So with very fast kinetics of going back and forth. In this case, we are quite sure that the transition is not first order anymore, because we see it in the formation and dissolution of the cluster.
And of course, you also do not have a uniform system, right? So it's a heterogeneous system. So you might even ask if something like a critical exponent is even meaningful in that sense, right? It's not a bulk system. Right?
It's not a bulk system, and the geometry of what is the system is odd, because it's confined on the base, and it's the feedback that confines. So when you have, let's say, something in a nanopore, you have a hard confinement. And in this case, the confinement is only coming from the feedback mechanism. It's not really confined. The bubble could expand, but it cannot, because it will run out of gas. So it's a very particular case of confinement.
Okay. Any other questions, comments? And if not, let's thank Valeria again for a nice talk.
Thank you. Thank you for the invitation.
All right, that was great.
Yeah, I'm going to close this. Again, thank you for